We want to continue exploring dissociation constants. We want to look at them within the context of conjugate pairs. So if you have a conjugate pair, right, remember the conjugate acid-base pair, molecules that are different by the H+ transfer. If you take the Ka of the conjugate acid and you multiply it by the Kb of the conjugate base, that will be equal to Kw. And that Kw is the equilibrium constant for the reaction of water with itself to make hydroniums and hydroxides. And so, for example, if I have HF and F-, the Ka of HF, that is 7.2 times 10 to the negative fourth. We could look that up. Kb of F-, we can look that up. 1.4 times 10 to the negative 11. We multiply those together, we get 1.0 times 10 to the negative 14th, which is the value for Kw. And so as a result of this, because we have this relationship, if you know, we can always predict if you have the acid what the conjugate base is, or if you have the base what the conjugate acid is. And so as a result, this relationship, we don't need to have tables of both Ka and Kb. So we've seen the tables of Ka previously. Those are what are always going to be available. They're just tables of acids, weak acids with all of their Ka constants that we have from experiment. We can take those and compute Kb. So you can find tables of Kbs, they do exist, but it's much more uncommon. It's usually more specialized for people who are using the same Kb over and over again. It's much more common to find really extensive tables of all of the weak acid dissociation constants, and then you can use this relationship to figure out Kb, because Kw is always 1 times 10 to the negative 14th. So if you know one of the dissociation constants, Ka or Kb, you can always compute the other. Let's do it. What is the Kb of CH3COO-? That is acetate, and I want to know the Kb of it. So what is the Kb of CH3COO-? So that is acetate. We can see it's an anion. That tends to indicate that this is probably potentially a base. We're dealing with Kb explicitly. We want to know how this thing behaves as a base. So when we've looked at Kas, we can use our table to look up the values for Ka. For Kb, there's generally not tables of Kb, there are tables of Ka values. But we can use the Ka values to determine the Kb values. And so what we can find is this is acetate, this is the conjugate base of acetic acid. And so we can look up that the related value, the Ka of CH3COOH, where it has the H, right, hasn't lost it, is equal to 1.76 times 10 to the negative fifth. And so these two things are a conjugate pair. And so what we know is that if you have a conjugate pair, the Ka of the acid in that conjugate pair times Kb of the base in the conjugate pair, those two values would combine to give you Kw, which is the equilibrium constant for water, right? The water cell autoionization. And so what we can do is if we want, this is what we want, right? So what we can do is we can take this value, plug that into there. That we can look up, or we know is 1.0 times 10 to the negative 14. And so we can plug those in. 10 to the negative fifth times the Kb of the conjugate of acetate by conjugate is equal to 1.0 times 10 to the negative 14th. And I find that Kb of my base is equal to 1.0 times 10 to the negative 14 divided by 1.76 times 10 to the negative fifth is equal to 5.7 times 10 to the negative 10th. And so we only really make tables of the Ka values, and we can use those to compute whatever Kb value we would potentially want. So we can always determine the Kb from this if we wanted to, or if we want to figure out what's going on or anything like that. We can always determine that information. So that's why we only tabulate Kas, and then you just kind of make everyone calculate KBs. Participation 225, question 2. What is the KB of hypochlorite, which is ClO minus? So what is the value of KB of hypochlorite? The second question on Participation 225 due Friday, February 25th at 11:55 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, what is the value of KB for hypochlorite, which is ClO minus? So with this relationship that Ka times Kb is equal to Kw, that Kw is a constant. That is always the same value. So what that means is that if we have Ka and Kb, when they multiply together, they always have to equal a constant value. So if one of them goes up, the other value has to go down. So for a weak acid that is relatively stronger, so we've looked at this relationship, H3PO4 is a relatively strong weak acid. That means its conjugate base has to be a relatively weak base. So the stronger the acid is, the weaker the conjugate is. And this is a generally true fact. So HCN, we saw, was our pretty weak acid. It really barely changed the pH. And as on the kind of opposite of that, Cn minus, its conjugate, is a relatively stronger weak base. And so it is going to be better at being a base than its conjugate. And these are always going to be opposites. So for a conjugate pair, the stronger one side of the conjugate is, the weaker the other one has to be. So they're going to be kind of opposites. If one is really relatively strong, then the other one has to be relatively weaker. So we can extend this out, and what it means if you have a really strong thing, so for example, a strong acid, its conjugate is so weak, it's not even a base. So this is what makes them strong. So for example, HCl is a strong acid, it's a very strong acid. Its conjugate, chloride, just is not a base. So if you have a strong acid, its conjugate is not a base. That means functionally it cannot, when it gets dissolved into water, it cannot produce any hydroniums. It cannot change, or any hydroxide, sorry. It cannot change the pH, right? It can't do anything. At the same time, a strong base, its conjugate is not an acid. Okay, so if you have something that's very strong, its conjugate is incapable of doing acid-base chemistry. So that sort of middle ground where you have weak, the conjugate of a weak acid is a weak base. So that's where you have the pair, when they're both weak at the same time. So you'd have, say, a weak acid, its conjugate is also a weak base. But a stronger weak acid, so for example, H3PO4, has a weaker weak base. They are still weak. They both can affect the pH, but H3PO4 does a better job of it. Up here, when you're dealing in the world of strong, one is really good at changing the pH, and the other one cannot change the pH at all. When they're both weak, they both can change the pH, just not necessarily at the same amount. So the middle ground, H2S, is one of the most middle ground bases, that Goldilocks, that perfect just right. So H2S is not very good at changing the pH, but not very bad. HS minus is not very good at changing the pH, not very bad. They are both kind of just middle of the road, kind of middle there, and so it's not really very good or very bad in the pair. But something like HPO42 minus is one of the weakest weak acids. It can barely affect the pH. You know, you get like a pH of like 6.5 versus 7, whereas its conjugate, PO43 minus, is a pretty good weak base. It's not strong, but it's a pretty good weak base. You know, you'd be pushing something like a pH of 11 or 12 as opposed to 13. So it can change it, but still, it is still weak. But there's always this kind of balance between them. And so if we look at what's going on here at a molecular level, so a strong acid, HCl plus water, HCl and water, this reaction goes all the way to completion because it's a strong acid. We got a single arrow there. And so what that means is that the reverse reaction doesn't happen. Chloride as a base, we could imagine what would happen in the reverse reaction is chloride reacting with hydronium to take a hydrogen proton away and recreate HCl. So if we put chloride into water, now you're thinking, can chloride take a hydrogen away from water? Well, chloride was incapable of taking a hydrogen away from hydronium, which is already not the most stable of ions. If chloride can't pull that hydrogen off of there, it certainly is not going to pull a hydrogen off of water. This reaction just doesn't happen. The equilibrium constant would be less than the autoionization of water, so water itself is a better base than chloride is. So water is doing more acid-base chemistry on its own than chloride. That's what we mean by chloride doesn't affect the pH of water, because the pH of water is already 7, because there is some acid-base chemistry already happening. So all of our strong acids, so the 6 strong acids that we have, all of their conjugates are not bases. In general, anions are weak bases, because anions can almost always take an H+. These 6 anions are the only anions that are not weak bases, because they are the conjugate base of a strong acid. So they're in a conjugate pair with strong acids. All other anions can be weak bases, not these 6, because the whole purpose of these is that they are really bad, basically, at taking H+ away from things. Bases take away H+, these things can't. If we look at the reaction of a weak acid, say acetic acid, so CH3COOH, if it reacts with water, only some of them will react to give an H+ to water. And one of the ways we can think about that is this equilibrium is reactant favored, right? It doesn't really happen. And one of the reasons is because the molecules on the product side are pretty good at doing chemistry, right? That reverse reaction happens relatively quickly. This conjugate base that we have right here, this acetate, the CH3COO-, is pretty good at taking is very good at taking H+ from hydroniums. So that's one of the reasons why we would have a reactant-favored equilibrium, is because those product molecules react really fast, right? We can get this kinetic description that reverse reaction happens really quickly because acetate is pretty decent at taking an H+ off of hydronium, which is a pretty good as far as acids go. So if we take that acetate and put it with water, this would be the conjugate base now, it's gonna be decent at doing that. Right? It was really good at taking it off hydronium. It's harder to take a hydrogen off of here because it has less, it's neutral, but it can do a decent job of it, leaving you with acetic acid, making that acid, and most importantly, producing the hydroxide. And so we can see that if you have a weak acid, its conjugate, if a weak acid, it's not really good at being an acid, but it can kind of be an acid. That means the conjugate also is okay at being a base. They're both just kind of okay, and they both have those properties. So this is something that's unique and special for weak acids, and why one of the applications that we need is that the conjugate can still do acid-base chemistry. So a weak acid, its conjugate is a weak base. That pair, they can both participate in doing acid-base chemistry. So all anions are weak bases as long as the conjugate acid is not strong. So that's most anions. Another participation question. See if we can find the rest of them. We're about halfway through, 306. See you in the next video.